Here we're going to define another function which is related with the density, with electronic density. This is a pair density. And it actually is going to involve the position of two electrons. And actually, as we'll see later, that's going to be related to the potential energy. So first, let's define what's pair density. So pair density is going to be the joint, that's going to be important, joint probability of finding an electron of a spin sigma at point R and another electron of a spin sigma prime at point R prime. So first, before having the expression of this pair density in terms of the wave function, we're going to we need the operator. Okay, as we did for the density. So this operator is going to depend on the two variables of the two electrons, r sigma, r prime, sigma prime. And it involves the position of two electrons. So we have different contributions. For example, here we have the contribution of being an electron I at position r and sigma spin state, and the electron j at position r prime and spin sigma prime. And then, as we have n electrons, what we have to do is we have to sum over different possibilities we might have for I, for j, of course, considering that I and j, they cannot be the same because they are different electrons located in different positions. Okay, and this is therefore the operator we have for the pair density. Now, once we have the operator and the wave function or the system stays, so what we can do, we have to do in order to obtain the expression for the pair density, we have to take the average of this operator, considering the state of the system is in this wave function. And in order to manipulate that expression, that's very easy to do. You have to follow the same steps we followed for the density. We have to express that as an integral over the different variables, the integration of the spatial coordinates of different variables, going from R1 to Rn. Then you have to do the integration of over the Ri and Rj variables, and the same with the summation of the spin states associated to I and j particles. So then you can manipulate and rename the variables r and r prime, so that but first, before doing that, you have to use that the wave function you have is antisymmetric. So if you change the position of two particles, then the wave function takes a minus sign, but as we are dealing with the square of the wave function, then it will remain the same. So dealing with that, it's quite easy to see that the different terms arising from the summation here, doing the summation over I and j, they are not going to be different. They are going to be the same, as it happened for the density. So actually, when doing this summation, you just have to sum over how many summations we are considering here. And the number of summations we are considering here is just n. So just considering that I, it's running from 1 to n, and times j, it's running from 1 to n again, but as they cannot be the same, so the number of summations for j will be n minus 1. So the number of total summations we'll have here is n times n minus 1. So that's why it's quite straightforward, but interesting to check that the final expression we have for that pair density, it's just the following: n times n minus 1, and then we have the expression after doing some refinement and for the pair density. Okay, this is the expression we have for the paired density in terms of the wave function. Okay, and as we said at the beginning, actually this paired density is going to be directly related to the potential energy, which is a two-body operator. So in order to see the relation between the potential energy and the paired density, you just have to go to the operator of the electron interaction operator. So the expression for the electron interaction is just this one. Okay, you have 1/2, just in order not to count the two particles twice, the summation over I and j, but without considering both to be the same, 1 over Ri position vector minus Rj position vector. Okay, that's the expression of the interelectronic potential operator, and as usual, we have to take the average, considering that the system is in this psi wave function. Okay, doing that, it's quite straightforward, but interesting to check that that's equivalent to this one. Okay, where we can write therefore the potential energy in terms of the paired density, which is here. Okay, just considering the definition before for the paired density, it's quite straightforward to see that the potential energy can be directly related to the paired density. And actually, the paired density we have here, as you can see here, we have a spin-summed paired density. So we are going to define another function which is related to the paired density, which is what's called the reduced paired density or the spin-sum paired density, which basically is the summation over sigma and sigma prime of the paired density, and just depends on the spatial coordinates r and r prime. So that's the reduced paired density. And as said before, actually the potential energy depends directly with this reduced paired density. And actually, often this reduced paired density is just called paired density as well. So here we have defined another density-related magnitude, which in this case depends on the position of two electrons. And that's actually quite interesting magnitude in the sense that it depends on the position of two electrons. It's going to be a very useful magnitude to analyze the correlation between the electrons.